Welcome to the quest of DeepSeek-V3.2, an effort to push the frontier of open large language models. The image sets up a classic David versus Goliath matchup. On one side, a smaller, scrappy contender labeled DS-V3.2. On the other, towering giants like GPT-5 and Gemini 3.0 Pro, glowing with power in a futuristic skyline. The point isn't just size, it's momentum. With strong research, smart engineering, and yes, a serious amount of GPU horsepower, open models are increasingly able to challenge the biggest proprietary systems. In this presentation, we'll explore what that takes, what's improved, and why it matters for the broader AI ecosystem. A big reason the gap kept widening comes down to three areas. First, architecture. Proprietary models pushed longer context and better efficiency, while many open models stayed tied to vanilla attention, which gets expensive and slow as sequences grow. Second, post-training. The best results often come after the base model is trained, especially with reinforcement learning and other compute-heavy tuning. Proprietary teams invested heavily there, while open models frequently couldn't match the compute budget. And third, agent skills. Turning a model into a reliable agent means strong instruction following, generalization, and tool use, knowing when to search, switch tools, and execute steps. Open models lagged here too, so the overall performance gap kept expanding. To scale to longer contexts, we first had to get attention much faster. In standard or vanilla attention, every query token compares itself to every other token in the sequence. That all-to-all pattern explodes in cost as the sequence grows, roughly O of L squared. Great for accuracy, but brutal for compute. DeepSeek sparse attention, or DSA, takes a smarter route. A lightning indexer quickly scores which tokens are most relevant, and then a fine-grained selection step retrieves only the top key value entries. So instead of attending everywhere, we attend where it matters, cutting complexity down to about O of L times K and making long context inference far more practical. Here's the big win. We significantly slashed inference costs, especially in long context use cases like 128K prompts. Think of inference as two main expenses. First is the pre-filling cost, processing that huge context up front, which used to feel like climbing a steep hill. Then comes the decoding cost, generating tokens step by step, which adds up over time. With DSA, we reduce both parts end to end, so the model spends less compute getting started and less compute finishing the response. The result is a noticeable speedup in long context scenarios and a big drop in per token cost, even on high-end hardware like H800 GPUs. Next, we really hit the gym with a scalable reinforcement learning framework. The goal here is to push capabilities further during post-training using a stable protocol called GRPO. Three ingredients make it work. First, an unbiased KL estimate helps keep the model anchored and training stable, so improvements don't come with unpredictable drift. Second, off-policy sequence masking filters out problematic or misleading training signals, so the model learns from the best parts of the data. Third, keep routing sends each prompt to the most suitable expert pathways, improving efficiency and quality. Together, these upgrades let us spend more than 10% of pre-training compute in post-training, where it can translate directly into stronger performance. All that training unlocked new abilities in two key ways. First is specialist distillation. Think of it like a panel of experts, math, coding, tool use, each contributing their strongest techniques. Those skills get distilled into a single model, so it can draw on expert-level patterns without needing separate systems. The second is mixed reinforcement learning training. Instead of teaching one domain at a time, we mix domains in a single training stage. That matters because multi-stage training can lead to catastrophic forgetting, where improving in one area accidentally erases progress in another. By training on a blended set of tasks, the model keeps more of what it learns and becomes more consistently capable across domains. To get an agent really good at real-world work, it needs a place to practice at scale. That's why we built what we call the Holodeck, a universe of automatically generated tasks and environments. Instead of training on a small, fixed set of examples, we synthesize 1,127 different environments and feed the agent 85 tools plus complex prompts. These prompts span very different skills, like resolving real GitHub issues for coding agents or planning multi-step trips with calendars, maps, and booking tools. The goal is to create diverse, challenging situations that drive reinforcement learning and, most importantly, improve generalization, so the agent can handle new tasks it hasn't seen before. Now for the main event, how these models perform on tough reasoning benchmarks in math and coding. On the math side, using AMI and HMMT, DeepSeek-V3.2 lands at 93.1 on AMI and 92.5 on HMMT. GPT-5 is close on AMI at 94.6, but lower on HMMT at 88.3. Gemini 3.0 Pro takes the top spot here with 95.0 on AMI and 97.5 on HMMT. For coding, measured by Codeforce's rating, the ordering is similar. DeepSeek-V3.2 at 2386, GPT-5 at 2537, and Gemini 3.0 Pro leading at 2708. The key takeaway is that DeepSeek-V3.2 stays competitive with top proprietary models on high-level reasoning tasks, reinforcing that open models can play in the same league. So the real question is, can these models actually take actions and finish tasks? Not just chat. That's what the agent arena is measuring. On the left, you can see many open source models struggling to get through the hurdles. DeepSeek V3.2 is a big step up, hitting about 73 on SWE verified and around 46 on Terminal Bench 2.0, which signals it can handle more realistic, tool-driven workflows. GPT-5 is slightly higher on SWE verified at roughly 75, but still drops on the terminal benchmark into the mid-30s, showing how hard end-to-end execution can be. On the far right, Gemini 3.0 Pro clears these tasks at near frontier levels, about 99 on SWE verified and nearly 99 on terminal bench, approaching agent master performance. After establishing a strong baseline, we pushed the next question. What happens if we encourage the model to think longer? The key lever here is the length penalty, which normally nudges the system to keep answers short. By dialing that penalty down, we make it less costly for the model to produce extended reasoning. That's the idea behind an experimental variant called DeepSeek V3.2 Special, or DSV3.2. It was trained exclusively on reasoning-focused data, and during reinforcement learning, we reduced the length penalty to promote more deliberate, step-by-step thought. The goal isn't verbosity for its own sake. It's to see whether giving the model more room to reason improves accuracy on challenging problems. DeepSeek just hit a major power-up with the V3.2 Special release. On this podium, Special takes the #1 spot, edging out Gemini 3.0 Pro and putting GPT-5 in third. The key takeaway isn't just wins a leaderboard, but what it implies: stronger, more reliable reasoning on tough math-style benchmarks. Look at the scores. On AMI 2025, Special posts a 96.0 versus Gemini's 95.0, and on HMMT, February 2025, it widens the gap, 99.2 compared to 97.5. In other words, Special is now competitive with Gemini at the top end, and it's outperforming GPT-5 in this evaluation set. Even when two models reach the right answer, the amount they have to say to get there can be wildly different. On the left, Gemini 3.0 Pro answers a simple question, like what is 2 plus 2, with a concise response. On the right, DeepSeek V3.2 Special gets there, but with a much longer, more elaborate explanation. That difference shows up in token counts too. Roughly 15,000 tokens versus about 23,000 on the same benchmark. The key takeaway is token efficiency. More verbosity can mean higher cost, slower responses, and less room for context. So improving efficiency is a major area worth focusing on going forward. We've made real progress, but the quest definitely continues. On the achievement side, we improved efficiency by slashing long context costs with DSA, so handling larger inputs becomes far more practical. We also pushed reasoning forward, reaching GPT-5 level performance using scalable reinforcement learning. And in terms of agency, synthetic data helped close key gaps, making the system more capable and reliable in complex tasks. Now the next challenges are clear. First, expand world knowledge to address the gaps that come from training with fewer flops. Second, improve token efficiency. getting more intelligence per token, so reasoning is denser and cheaper. And third, solve even harder problems by refining both the model and the post-training recipe. If you want the complete story behind what we covered, here's where to go next. The work comes from the team at DeepSeek AI, and the best way to really understand the design choices, experiments, and results is to read the original paper. You can scan the QR code on the left to open the ARAR hierarchive preprint ID 252.0256V1 and dive into the full technical write-up. And if you'd rather explore the model artifacts directly, the QR code on the right takes you to the Hugging Face repository, listed as DeepSeek AI DeepSeek-V3.2 ext. Between these two links, you'll have both the theory and the implementation at your fingertips. If you're the kind of person who reads the appendix of a slide deck, first of all, welcome. That little joke on the screen makes a serious point. The appendix is where the why lives. It's where we park the extra evidence, definitions, assumptions, and edge cases that don't fit neatly into the main story, but still matter for trust and transparency. So if a claim in the core slides raises a question like, how was this measured? Or what data supports this? The appendix is your map. Use it to validate the conclusions, understand the limits, and go as deep as you need.